Assalamu alaikum. So today we will discuss a new subtopic. So in our previous classes doing we were discussing about a BJT, bipolar junction transistor. So today we will start FET. So FET is field effect transistor, and under that we have JFET. So that is what we have in our syllabus. So that is junction field effect transistor. Junction field effect transistor. So first I will completely explain how this junction field effect transistor is going to work. After that, let's write down the note. So in junction field effect transistor, we call this one as unipolar device. BJT, this B stands for bipolar, right? So why it is bipolar? A BJT, the current was due to, or the current flow was due to both electrons and holes due to majority carrier and as well as minority carrier. But here, this JFET, it is going to conduct electricity only due to the majority carrier. Therefore, only one of them, may be the electron or the hole. One of them is going to conduct the current. Therefore, it is called as unipolar. Okay, so this is a unipolar device. Then, in this unipolar device, we have a few sections. We can divide this into now in our syllabus we have to talk about n-channel JFET. Okay, n-channel JFET. So this channel, this is where the current is going to flow. Therefore, this part, this channel is made up of n-type material. So this is made up of n-type material, and here this is made up of p-type material. So this is made up of p-type material. So this is n-type and this is p-type. Here we have a small metallic connector which will connect the external circuit to this N channel, and here it will connect out of this N channel. So we call this is the drain. And this is the source. And these two P region, they are connected together. They are connected together. So they are connected together and taken out as a single terminal. And we call this terminal as the gate. So this is the drain terminal, this is the source terminal, and this is the gate terminal. So here, the current is going to flow from the drain to source. Or otherwise, let's say, let's talk about the electron flow. Electron is going to flow from the source to the drain. So the name suits, right, for this terminal as the source, because the electron is going to start from here. So the electron will move up in this direction. So here in this, we have only a PN junction. We have only one PN junction. So this PN junction is always reverse biased. We will reverse bias this. When we reverse bias this, around this, it will form the depletion layer, which will block the flow of current. Okay, so that's the basic idea. We will look in detail when we are discussing this part. Okay, so first draw this diagram. So this is a ohmic connector. And this is a N-channel JFET. JFET is a unipolar device. Is a unipolar device. Since the current is carried either by electrons or, that is very important, or holes. Not both of them, one of them. So we are going to control the current. We are going to control the current by controlling this depletion layer. And this depletion layer is controlled by a voltage source between the gate and the source. We will discuss that. So anyhow, this depletion layer is controlled by a voltage source. That means an electric field. That is why we tell this one as a field effect transistor. Okay, because the current flow between the current flow between the drain and the source is controlled by the action of electric field, controlled by the action of electric field at the PN junction, at the PN junction. Hence the name, field effect transistor. Okay, hence the name field effect. The action of the field, the action of the electric field is controlled by the voltage source, by the uh, voltage source, between the gate and the source terminals. Thus, this is a voltage control device. Thus, this is a voltage control device. Mm, we gave an introduction about BJT, right? Not here. Under BJT, can you add another point that BJT is a current control device? Under operation of BJT, finally include this point that BJT is a current control device. Why is that? We are controlling the IB current. By controlling the IB current, I can control the output IC current. Okay, so BJT is a current control device. Include that in the note. Under operation of transistors and operation of BJT, finally, I think we wrote that IB, IE is equal to IB plus IC. Below that, write this. Okay, done. So JFET, we can classify JFET as N-channel JFET, N-channel, and P-channel. N-channel and P-channel. So in N-channel, JFET, channel channel made of N-type material, and in P-channel, channel made of P-type material. And in N-channel, who will conduct the current? The majority carrier, that's the electron. Electron conducts the current. And in P channel, holes are the majority carrier. Therefore, holes conduct current. And the symbol drain source. So uh, if the arrow is inward like this, if the arrow is in, that means this is N channel. How to get it? So always this arrow points from P to N. So this is P and this is N. The channel is N. We can otherwise show this one as close to the gate. Okay, this arrow close to the source. This gate is close to the source. If it is the other way, so this is P channel, P, N, so channel is P. Or we can show close to the source. Next subtopic. construction construction of uh, n-channel JFET. N-channel JFET. So in an n-channel JFET, we have the same diagram as above. Therefore, I'm not drawing once again. We will describe based on that. Okay. Two ohmic conductor, two ohmic connections are made. Connections are made at the ends of an extrinsic n-type bar, which is the drain and source, which is the drain and source. Heavily doped p-type material, makes the PN junction on either sides of the bar. The thin layer between the two gates is the channel. Since the channel is made up of n-type material, this is and these are n-channel JFET. N-channel JFET. The electrons enter from the source and leave from the drain. Hence the conventional current is from drain to source. The p-type material is connected together and taken out as a as a single terminal as a single terminal, and this is the gate, and this is the gate. Next topic, operation of a JFET. Once you have noted to this, let me know. So yeah, done. Okay, now let's look how this JFET is going to work. Sorry, the same diagram down. Now let's connect a source to VDD. VDD, source VDD. So just don't worry about the names, okay? VCC, VDD, that is just the names given to the source. So this is VDD, and this is drain D, this is source S, and this is gate. Source S and gate. Now we can control this PN junction by applying voltage between gate and source. But we have to apply, we have to have a reverse bias. Then only the depletion layer will get larger. So how can we have a reverse bias? To have reverse bias, we must connect the negative side to P-type and the positive side to N-type. So we have to connect a battery in this manner. Negative side to P and positive side to N. Now this will get reverse biased. Initially, to understand what is happening here, first let's not reverse bias this, okay? I'm not going to reverse bias. Instead, what I'm going to do is, I'm going to just short circuit it. I'm going to keep the source, I'm going to keep the gate and the source at 0. Or let's say this is VGS, okay? So VGS is negative. Sorry, VGS is 0. So this is a variable source. When VGS is 0, when VGS is equal to 0, now we are not reverse biasing this. We are not reverse biasing these 2 points, okay? It is just kept at 0 volt. Now, when this is zero voltage, initially there is no any reverse biasing. There is no any reverse biasing, and we have connected a source. Therefore, current will start to flow. A current will flow from drain to source. Okay, current will flow from drain to source. This portion, this region just acts like a resistor. So it is just like a continuous resistor. So in a continuous resistors that are connected in series. So we know when current passes through a resistor, there will be potential drops. Okay. Now this is earth. This is earth. So this is at 0 volt and this is at a higher voltage, some higher voltage VD. Then only current will be flowing down. So when the current flows down, here at these points, you're going to have a lesser voltage than this, but a positive voltage. You're going to have positive voltages. Okay, here the voltages are positive in each point. And this is the P region. So what is the voltage of this P region? That is 0 volts. That is 0 volt because VGS is 0. Because this is 0 and this is at a higher voltage, what can you tell about this region? Is it forward biased or reverse biased? Is it forward biased or reverse biased? Over here. So this region, now I have drawn, the current is flowing down through the N channel. So this is the N channel. Okay. I said when current is flowing down, this region acts like a continuous resistor, just like a resistors that are connected in series. And here we have this P-type region, and this one represents the N-type region. So I am asking this region, what is happening over here? Is it reverse biased or forward biased? Okay, Sarah, did you get the question? Sorry, Saja, did you get the question? So here, over here, this is actually reverse biased. It is reverse biased. How is it reverse biased? Now, can you remember when I want to reverse bias a junction, what I actually do is I want to connect, I want to connect this to a negative voltage and this to a positive voltage. Is that the actual way? No, it is like this. I can connect them, both of them to the positive voltage, but the P-type should have a lower voltage, just like this. Now, is it reverse biased or forward biased? This is now reverse biased because N-type has higher voltage, P-type has low voltage. Therefore, this is reverse biased. Okay, got that idea? So, over here, over here, now this is at 0 volts. If this is at 0 volt, the voltage uh, in this region has to be greater than 0. And P-type is connected to 0. N-type is having some positive voltage. Therefore, this region is reverse biased. Got that idea clear? And it is not uniformly reverse biased. The region close to the drain is more reverse biased than the region close to the source. Just like this. Wedge shaped. Like this. The reason is here you have higher voltage. For example, let's say our VD is 10 volt or VD is 10 volt. And here we might have 6. Here we might have 5. Here it's 4. So this region is more reverse biased. Therefore, the depletion layer is larger. When it comes down, it is smaller. Over here, it's even small. So you get a wedge shape. You know a wedge, right? So it gets a wedge shape. Is it clear why we get a wedge shape? Now, this voltage, now it should be clear for this wedge shape to become stronger or for this depletion layer to become broader, the VD has to increase. For smaller VD, for smaller VD values, this junction or this reverse bias or this depletion layer is very small. Therefore, it won't affect the current flow. But when it is getting larger and larger, the current flow will start to reduce. Okay, the current flow will start to reduce. So if we show it in a graph, IDS versus VDS. Okay, IDS versus VDS. The voltage between these 2 points versus ID. Initially, it is not affected. It is not affected. But as VDS increase, as this VD increase, now this reverse bias effect gets stronger. Therefore, the current reduces and after some time it will become constant. Now, this part, up to this part, you must be clear that the current will reduce. The current will reduce. And now you might have a doubt, why does it become constant without it completely closing this junction? So just think, if it completely closes the junction, then the current flow becomes zero. If the current flow is zero, then there won't be potential drops. If there is no potential drop, again, this junction will become open. Therefore, this current cannot become zero. Okay, that current cannot become zero. So both of them come to an equilibrium level. The amount of the junction closing and this current. The junction cannot close further, the current cannot increase further. Got it? Sarah and Saja, did you get the idea? Sarah, the final one. The current cannot increase further. The junction also cannot close further. Okay. I will upload this note to the group. I'll go quickly pray and come. So in that gap, you can get the note copied, right? For the part I explained.